This video is going to have a look at the understanding and explanation behind the slightly strange shape of heating and cooling curves. In this video we're going to focus on the example of water because it's one of the common examples you might come across. So first of all, let's draw a heating curve for water. And you'll notice on the left hand side, the y-axis, we have temperature, in this case in degrees Celsius. Along the bottom on the x-axis we have energy input or heating time. So we're effectively heating my substance consistently and measuring the temperature as we go along. The first thing to notice is that we can kind of break this graph into 5 sections. The first section is increasing, the second section is flat, then increasing, and then flat, and then increasing again. And I'm going to add a little diagram to show what we'd actually observe in this process. And we're starting off with a cube of ice, and obviously to measure the temperature I need a thermometer stuck into my ice cube. At the flat part of the curve, it's when I will actually start to notice my ice cube melting. On the next section of the curve, we find that all of the ice has melted and I now have liquid water. That's clearly increasing in temperature. And then again, when I get to about 100 degrees, or the boiling point of water, I'll notice that my water starts to boil. I'll see bubbles forming throughout the solution as it begins to turn into a gas. And again, the final part of my curve where it's now increasing again, we're actually now dealing with just gaseous water or water vapor. So what we need to try and do now is explain why we get such an unusual shape to the curve, i.e. why does the temperature not just keep increasing as I heat my ice cube? So to do so, let's consider the actual particulate structure. In this case, the blue particles are representing molecules in my different substances. So when we have water in the solid form or ice, you can see the left-hand diagram. My particles are in a fixed position and vibrating. So what happens when I start heating my ice cube? Well, you'll notice that the temperature starts increasing. And when temperature increases, what that's telling me is that the average kinetic energy of my particles is increasing. So in that part of the curve, we still have an ice cube. It's not started melting yet. My particles are just going to start vibrating faster and faster and faster. So their kinetic energy is increasing. Now, the observation we made at the first flat point of the curve was that my ice cube starts to melt. And you'll notice at this point, the temperature is actually not increasing. So the energy I'm inputting or heating my ice cube with is no longer increasing the kinetic energy. So what is it doing? Well, of course, if I want to get from my solid ice cube to liquid water, I'm needing to overcome some of the intermolecular forces between my water molecules. So at this part of the curve where my ice cube is melting, what's actually happening is the energy I'm providing to my ice cube is now being used to partially overcome those intermolecular forces. It is not increasing their kinetic energy, it is only overcoming those intermolecular forces to allow the water molecules to move freely. Once my entire ice cube has melted, then the energy I'm inputting can again be used to increase the kinetic energy of those particles. So in that middle diagram, my particles I would expect to see moving faster and faster. They're still close together because it's a liquid, but their speed is going to be increasing. We then get to a second flat point on the curve, and this one you might remember is about 100 degrees, which is the boiling point of water. And again, it's flat, meaning that the energy I'm inputting is not increasing their kinetic energy. In this case, it must be being used in the boiling process, which requires energy completely overcoming the intermolecular forces so that those particles can now move freely and far apart from each other. Once all of my liquid water has been turned into a gas, at the end of the red section there, you'll then see the temperature start increasing, suggesting that the kinetic energy of the particles is once again increasing. So in my diagram, I would expect to see those gaseous particles or water molecules moving faster and faster and faster. And that's pretty much it. We need to know the kind of flat bits of the curve are where energy is being used to partially overcome and then fully overcome intermolecular forces. And the steep parts of the curve is simply showing that the kinetic energy of my particles, or water molecules in this case, must be increasing. So just to touch briefly on a cooling curve for water, we would actually expect to see effectively the same thing but in reverse. So in this case, I would be starting with a hot gas and cooling it. And as you can see, the first section of my graph is a decreasing gradient, which must mean that the kinetic energy of my gaseous particles is decreasing. When I get back to that boiling point or condensation point, if I'm going in the opposite direction, we must recognize that at this point here, my intermolecular forces are effectively regaining control of the molecules, which is why their kinetic energy stops decreasing while those intermolecular forces are kind of reforming. Once all of my gaseous water molecules have condensed into a liquid and I continue to cool that liquid, you'll notice the temperature keeps dropping, therefore the kinetic energy of those water molecules is decreasing until I get to 0 degrees, which is the melting point or freezing point if we're going in this direction. And again, why does the kinetic energy of my particles stop decreasing? Well, actually, those intermolecular forces are now gaining full control of those molecules and holding them in a fixed position. Again, once all of my liquid water molecules have turned into the solid state or ice, and I continue to cool it, well, I can see that the kinetic energy of those vibrations is going to keep decreasing again. And that's pretty much it for heating and cooling curves. We just need to be able to describe what's happening at the flat sections and what's happening at the steep sections. Hopefully this video is of some help.